Ladies and gentlemen, welcome back to this course in group theory. In this course, we've seen a lot of groups, one of which was the symmetric group in lesson 5. I highly recommend you check that out, as it is a very interesting group of permutations of a set. The permutations could be represented by cycles, and this greatly reduced our computations in, for example, computing the composition of two cycles. But what if I told you there is a way to classify the cycles and the permutations in Sn? Well, this way is called the permutation matrices, which can represent each and every cycle. And this will enable us to classify the cycles and define what is called the alternate group. So this will be the topic of today's video. Let's get started. We immediately start with the definition of the matrix representation of a permutation. Let E be the set containing 1 through n, and sigma be a permutation lying in SE, which is commonly known as Sn. The permutation matrix L sigma, L subscript sigma, associated to sigma, is the n by n matrix in R defined by, so it's defined by the entries which are given in each row column in L sigma. So for the ith row, the jth column, we denote the entry by L sigma ij, and L sigma ij is defined to be equal to either 1 or 0. It is equal to 1 if sigma of j is equal to I, and 0 if sigma of j is not equal to I. So to use this definition in filling out our permutation matrix, this is how we will fill it out. We will go column by column. For each column, we will see where sigma sends the jth column. If sigma sends jth column to the ith row, and we go to the ith row and we write in ij, we write the number 1. Because sigma sends j to a single I and nowhere else, all the other rows in the same column have to be equal to 0. So we will have a single 1 in the column, and all the other rows in that column are equal to 0, and we repeat the process for each column in the matrix until we have fulfilled our permutation matrix. To see how the problem of permutations can be translated very well into the problem of linear algebra, let EI be the unit vector that contains 1 in its ith component and 0 everywhere else. Then we see immediately that E of sigma I is equal to EI when multiplied by the permutation matrix of sigma. So you can see a very neat description of where sigma sends the 1 to. So if 1 is in row 3 and sigma sends it to another row, then we will see that take effect in the vector of EI. Now, if sigma and tau are in SE, then we can describe their composition by another matrix, which is also a permutation matrix. So let us see that this composition matrix is in fact L sigma tau, which is equal to L sigma times L tau. We will see that this is in fact the permutation matrix that gives us E sigma tau I. So we have that L sigma L tau, when applied on EI, by associativity of matrix multiplication, we can say that this is equal to L sigma times L tau EI, and L tau EI by definition is equal to E tau I. So this is L sigma times E tau of I, and we use the definition again to get back E of sigma of tau I. And E of sigma of tau I is equal to E of sigma composed with tau of I. Therefore, proving that this matrix multiplication L sigma times L tau is in fact equal to L sigma composed with tau, because it gave us exactly that this multiplied by EI gives us E sigma composed with tau I. Let us now have a look at an example. Let E be the set containing 1, 2, and 3, and SE be just S3 in this case, because we have 3 elements. Consider sigma being the cycle 1, 2. So sigma is a permutation in S3. So that means that sigma sends 1 to 2 and 2 to 1 and 3 to itself. So sigma of 1 is equal to 2, sigma of 2 is equal to 1, and sigma of 3 is equal to 3. So let us fill out the permutation matrix of sigma, L sigma. It's a 3 by 3 matrix because we are in S3. And let us look at the first row. In the first row, we have that sigma of 1 is equal to 2. So we're going to write 1 in the second row and 0 everywhere else. So 1 in the second row and 0 everywhere else. Now we repeat the process for the second column. In the second column, notice that sigma sends 2 to 1. So we write a 1 in the first row and 0 everywhere else. In the last column, we have that 3 is sent to itself, so we're going to put a 1 in the third row and 0 everywhere else. So 1 in the third row and 0 everywhere else, thus giving us L sigma, which is the permutation matrix associated to sigma, which is the cycle 1, 2. Consider now another permutation in S3, which is called tau, which is defined to be the cycle 3, 2, 1. So tau of 1 is equal to 3, tau of 2 is equal to 1, tau of 3 is equal to 2. By the way, if you're having difficulty understanding these concepts, I would encourage you highly to go back to lesson 5, which is symmetric groups, to understand more about how cycles and permutations work. Now, L of tau is the matrix that represents tau, and in this case, we will follow the same procedures that we did for sigma. In the first column, we have that 1 is sent to 3, so we write 1 in the third row and 0 everywhere else. In the second column, we have that tau of 2 is equal to 1, so 1 goes in the first row and 0 everywhere else. And in the third column, we have that tau of 3 is equal to 2, so 1 goes in the second row and 0 everywhere else, thus completing the description of the permutation matrix L tau. To see what L tau does to the second element, so tau of 2, consider the permutation matrix L tau multiplied by the vector E2. So if we multiply L tau by E2, we will expect to have E1, since 2 is being sent to 1. So let us verify this. So in the first row, we have that 0 times 0 plus 1 times 1 plus 0 times 0 is equal to 1. And you can verify by yourself that the other rows are equal to 0, thus giving us, as expected, E1. Thus enforcing the idea that L tau is in fact the permutation matrix for tau. Let us explore now what happens when we combine sigma and tau together. When we compose these two permutations, we expect to get their composition the same way we would multiply their cycles together. If we multiply the cycles sigma and tau together, we would get something like 1, 2, which is sigma, times 3, 2, 1, which is tau, giving us 1, 3. So multiplying L of sigma times L of tau should give us L of sigma composed with tau, which is L of 1, 3. Let us verify this fact. With a bit of computation, we see the following. So it gives us this matrix over here, and let us verify that it's indeed L of 1, 3. So in the first column, it is sent to the third row. In the second column, it is sent to the second row, and in the third column, it is sent to the first row. So 1 is being sent to 3, 2 is being sent to 2, and 3 is being sent to 1. So in fact, this is equal to exactly L of 1, 3, which is L of sigma composed with tau, thus confirming our intuition that the permutation matrix is a complete representation of the permutation. Now that we have seen that each permutation in the group Sn can be represented by a specific matrix that is unique, it is time to classify each of these permutations according to their permutation matrices. To do that, we will introduce several important notions that are very relevant, and we will use these facts to classify these permutations. One of those classifications is going to be the group which is called the alternate group, AN. Let us start with a lemma that says every permutation matrix has a determinant of either 1 or -1. So to prove this lemma, if you know your linear algebra well, we can perform row operations on any matrix to go from a certain matrix to another matrix, and then we can multiply certain factors by the determinant to obtain the determinant in an easier way. So in fact, this is what we're going to be doing. So I will write that every permutation matrix L can be changed to the identity matrix I by performing a finite number K of row exchanges, going column by column so that K is minimal. Let me explain this statement. We have that a permutation matrix looks something like this: 0, 1, 0, 0, 0, 1, 1, 0, 0. Since we have the matrix composed of only zeros and ones, where we have a single 1 in each row, it is possible to perform row operations, more particularly row exchanges, to go from this to the identity, which is 1 on each entry in the diagonal and 0 everywhere else. And we know for a fact that the determinant of this matrix is equal to 1. And we know that row operations serve only to change the sign of the determinant each time a row operation is made. So, in fact, this matrix, when we perform the row operations and we end up with the determinant being 1, we have that the sign of 1 changes from positive to negative and to positive again, depending on the number of times we have to perform the row exchanges until we get back the identity. So in fact, it is equal either to 1 or to -1 and no other number. We want to ensure that the number of row exchanges does not go on forever, so we will choose a minimal number of row exchanges going column by column, so to ensure we don't have any repetitions going on. So to make this idea more formal, let L be equal to L0, and then we have L1, L2, all the way to Lk, which is the identity. So this is a sequence of matrices where each matrix is produced by performing a single row exchange. So we have the recurrence relation, the determinant of Li plus 1 So the determinant of the I plus 1th matrix in the list is equal to minus 1 times the determinant of the previous matrix in the list for all I between 0 and k minus 1, since each row exchange induces a multiplication of minus 1. So for each row exchange, we will multiply the determinant of the previous matrix in the sequence by minus 1 until we reach the last element, which is LK here, and that equals the identity. Thus, by induction, which I leave to you as an exercise, we can prove that the determinant of L is equal to minus 1 k times determinant of the identity, which is minus 1 to the k times 1, which is equal to minus 1 to the k. So we have a minus 1, and then we repeat the process to have another minus 1, and then another minus 1 in the product, and then another one, until we get k times of these, which we multiply by the determinant of the last matrix in the sequence. And that is equal to minus 1 to the k, but minus 1 to the k is either 1 or minus 1, which completes the proof of our lemma, saying every permutation matrix has determinant 1 or minus 1. If this lemma was a bit confusing, don't worry, we will go through an example to make it clear. So we will go back to the original example that we've seen in S3 and the same sigma and tau. So sigma is 1, 2, and tau is 3, 2, 1. We have seen both the matrix representations of sigma and of tau. So we want to find the determinant of these matrices. To find the determinant of these matrices, we will perform row operations till we get the identity I, which is 1, 1, 1. So L sigma is equal to 0, 1, 0, 1, 0, 0, 0, 0, 1. We find that the only one that is in its right place is here, same way as in the identity, but we have that this is not in its right place, and neither is this. So we want to perform row operations until all of the ones are where they should be. So we will exchange rows 1 and 2 to get back the identity element. And in the table here on the right, we find that k here is equal to 1 for a single row exchange. And for L tau, we have that this one is not in its right place, and neither is this, and neither is that. So to fix that, we need to perform two row operations. The first row operation, going by the first column, is we want to put this one up top. So we want to exchange rows 1 and 3 to get back this matrix. And then after having done that, we want to look at the second column and see that this one has to go over here. So we want to perform the second exchange to get back finally the identity matrix. And now we've seen that we need two row exchanges to reach the identity, which makes k is equal to 2 for L tau. So to calculate the determinant, we have that determinant of L sigma is minus 1 to the power of k, which is 1, equaling minus 1. And the determinant of L tau is minus 1 to the k, which is 2, which is equal to 1. So now we know that the determinant of a permutation matrix is going to be either 1 or minus 1. So the natural question that arises is, can we classify those matrices with determinant 1 and those with determinant minus 1? In fact, this is the whole purpose of today's lesson, is to classify the matrices on this basis. So to put it formally, we will define what is called a sign map that will give this sign. Is it positive? Is it negative? So positive 1, negative 1 for the determinant, So the sign map is defined as SG, taking a permutation and giving back a non-zero complex number. Now I'd like you to be not too intimidated by the C star codomain, because we will not really have any complex numbers as our determinant. We have just proved that the determinant of a permutation matrix is either going to be equal to 1 or minus 1. So in fact, the codomain is way larger than the image. So here we have that the sign map is in fact a group homomorphism. And this fact comes immediately from the fact that the determinant is a homomorphism. We will see this now. So if sigma and tau are elements in Sn, we have that the sign sends sigma and tau to, formally, we have this is equal to the determinant of L sigma times L tau, and this is equal to the determinant of L sigma times the determinant of L tau, because determinant is a homomorphism, and this equals, in fact, by the definition of the sign map, to be sine of sigma times sine of tau, thus proving that sine is, in fact, a homomorphism. Now, if sine sigma is equal to 1, the permutation is called even, an even permutation. If the sign map gives a minus 1, the permutation is an odd permutation. The set of even permutations of order n is called the alternate group, which is called by a notation of an. So now we have Sn, the set of all the permutations of a certain set, and we have now the set of even permutations of the order n to be an. Now that we have defined that the sign map is a map that takes a permutation in Sn and goes to the multiplicative group C star. So remember that C star is a multiplicative group. In other words, a group with the operation being multiplication, and the identity has to be equal to 1 in this case, because 1 is the multiplicative identity. So the kernel of the sign is all the permutations, such that if we take the sign of their permutation matrix, we will get back 1. In fact, 1 is the identity of C star, and this would be, in fact, the exact definition of what the alternate group is. So it's exactly the permutations in an, and I leave that to you as an exercise to formally prove that the kernel of the sign is an. Now, another remark is that every permutation in Sn can be written as a product of two cycles, and any two cycle we call a transposition. Because if we have a cycle like this, A1 to AK, we can write it as A1, A2, A2, A3, A3, A4, all the way until AK-1, AK. And in fact, these two sides of the equation are equal because they will send A1 to A2, A2 to A3, A3 to A4, and AK back to A1. The last part, I need you to verify. I need you to verify that this side here will send AK back to A1. Now, another thing that we remark is that if we take the sign of a transposition, we always get back -1. Because in a transposition, we are doing a single row exchange until we get back the identity matrix. So if we do a single row exchange, the sign gives us -1 to the power 1, which is -1. So because the sign of a transposition is -1, we can look into the sign of any cycle to be the product of the sign of its transpositions, because any cycle can be decomposed into transpositions like that. So the sign of a cycle like this can be equal to the sign of the product of its transpositions. And because sign is a homomorphism, we can split them up like this. And each of these signs is equal to -1. So in fact, it is dependent entirely upon the number of transpositions that the cycle is made up of. So now, since every permutation in Sn can be decomposed into different cycles, a 2-cycle, a 5-cycle, a 7-cycle, and so on, and since every cycle can be decomposed into transpositions, as you've seen here, and since every transposition has a sign of -1, we can characterize every permutation in Sn by transpositions. So we will look at the sign of each transposition, we will count the number of transpositions, and this will give us information about whether sigma is an even or an odd permutation. So let us start with just k-cycles. So sigma is in a k-cycle. So if sigma is a k-cycle, it's an an, the alternating group, if and only if sigma is an even permutation. It's just another way of saying sigma is an an, if and only if the sign of sigma is equal to 1. The sign of sigma is equal to 1 if and only if -1 to the k-1 is equal to 1, because this is in fact equal to the sign of the k-cycle sigma. So we need for k-1 to be even, for -1 to the power of an even number to give us 1. So this is if and only if k-1 is even. And we know that there are k-1 transpositions in a k-cycle. So there are k-1 transpositions in the cycle decomposition of sigma. So there is an even number of transpositions in sigma. And this in general applies not only for a k-cycle, but for any permutation in Sn. So sigma is an an if sigma contains an even number of transpositions in its product decomposition. So if sigma is a 3-cycle, then sigma is even. If sigma is a 6-cycle, 6 elements in a cycle, then sigma is an odd permutation and it does not belong in An. For example, we have the cycle 1, 2, 3 in S3. Let us consider 1, 2, 3. How can we write 1, 2, 3 as a product of transpositions? Remember, a transposition is a 2-pair, and we want to turn this 3-pair into a product of 2 pairs. So the simplest way to do that is just to write 1, 2 and 2, 3. And you can verify yourself that this is in fact equal to 1, 2, 3. The sign of 1, 2, 3 is going to be -1 for 1, 2 times -1 for 2, 3, which turns out to be -1 squared. And remember, 2 is equal to k-1, where k is equal to 3 because we have 3 elements in the cycle, and 1, 2, 3 is a 3-cycle. So -1 squared is equal to 1. So 1, 2, 3 is inside An because the sign is equal to 1, not -1. Let us look now into another example, which is 1, 2, 3 composed with 4, 5. So we will treat each cycle separately. We treat 1, 2, 3 first, and we treat 4, 5, and then we combine them together. So 1, 2, 3 is again 1, 2, 2, 3, and 4, 5 is just 4, 5. So the sign can be decompose because it's a homomorphism into the sign of 1, 2, 3 and the sign of 4, 5. And the sign of 1, 2, 3 is just the sign of 1, 2, sign of 2, 3, and the sign of 4, 5. And this equals to -1 times -1 times -1, which is equal to -1. And this makes sense because earlier we said that 1, 2, 3 is an even permutation, so it was equal to 1. But once we added a single transposition to the mix, we had to multiply the product by -1, and thus we have -1 as a result. So we conclude that 1, 2, 3, 4, 5 does not belong in the alternating group because the sign of this element is equal to -1, which is not the identity of the multiplicative group C star. And this completes the lesson. I really hope that you enjoyed, and I'm really excited to share with you more on group theory in the future lessons. Please like, subscribe, share with your friends who are interested in this topic, and I'll see you on the next time. Have a nice day.